Hi everyone, I'm Elisa Goffo and I'm a PhD student at the University of Torino and at the Thüringer Landessternwarte Tautenburg. And today I'm going to talk to you about GJ367 system and its ultra high density, ultra short period sub-Earth. So to start, GJ367, it's a hem-draw stars that was observed by TESS during its primary mission in 2019. And TESS observed this transiting signal at 7.7 hours. In 2021, Lam et al., they confirmed a high-density ultra-short period sub-Earth with 77 ARPS radio velocity observations. So here, some stellar parameters about the star. We have these M-dwarf stars at 9 parsec, with the mass and radius of about 45% the mass and radius of the sun. And here, the planetary parameters found by Lam et al. For the ultra-short period planet. So the period of 0.32 days, a radius of about 0.7 Earth radii, and a mass of 0.5 Earth masses. So this resulting in a very high density of about 8 plus minus 2 grams per cubic centimeters. And they performed some interior structure models predicting an iron core mass fraction of 86%. The system was already like this very interesting because we have this ultra short period, small planet, super dense, but we decided to keep observe the star and in order to unveil the architecture of the system. So we obtained more than 290 new radio velocities with ARPS for a total of 371 radio velocities in a baseline of almost 3 years. So thanks to all these new measurements, we were able to first refine the planetary parameters for this USP planet, but also discovering other 2 planets around the system at 11.5 days and at 34 days. So now let's have a look at the analysis that we performed in our work. So here I presented the frequency analysis. On the left, you have the radio velocities. On the right, the activity indicators. And so in the periodograms of the radio velocities, we found 5 different signals, significant signals. First one at 11.5 days, at 34 days, at 51 and 115, and as expected, also a significant signal at the orbital period of the transiting USP planet. So then we also compare this with the periodograms of some activity indicators like chromaticity index, differential light width, H alpha, log RHK, and the sodium doublet. So first of all, for the 2 signals highlighted with red dotted lines at 11.5 days and 34, we didn't find any significant peaks in the activity indicator, suggesting that these 2 signals are induced by the presence of other companions, other 2 companions in the system. In the case of the 2 signals highlighted in yellow at 51 and 115, we saw some counterparts in the activity indicator, suggesting that they are linked to the stellar activity. So in particular for the signals of 51 days, we found that this is an agreement also with the modulation that we found in WOS photometry at 48 days, and also with the rotational period that we estimated from the log RHK rotation relationship for M-dwarf. Let's have a look at, in particular, the analysis that we did for the USP planet. As I said, we obtained these new radio velocities between 2020 and 2022. And in the meantime, TESS also reobserved the star. This allowed us to have more TESS photometry with increased cadence. So we performed this joint analysis of TESS transit light curves with ARPS radio velocities. And in particular, for the radio velocities, we use this floating chunk offset method. So briefly, we considered that in a single night of observation, the the radio velocity variations of the star is mainly induced by the presence of this inner planet, of this USP planet. And we can treat other signals at long period, like signals due to other components or cell activity or magnetic cycle as constant. So here are the results that we obtained in this work compared with the previous result of Lam et al. So now we have a mass of 0.6 Earth masses, a radius of 0.7 Earth radii. And as you can see, we improved a lot the precision on the estimation of the mass and radius. And we derived a density of 10.2 plus minus 1.3 gram per cubic centimeters. But obviously, to model the two other signals due to the planets and to estimate the radio velocity, semi-amplitude of the other planets, the floating chunk offset method cannot help us. So we performed this multi-dimensional Gaussian process approach. We consider 2D GP model, modeling the radio velocity time series with one of the activity indicator that showed one of the highest peak related to the cell activity, and this is the differential and width. We use a quasi-periodic kernel, and here are the results. So I want to highlight the results, the semi-amplitude and the minimum mass that we found for the two other planets at 11.5 and 34 days. So we found this minimum mass
of a package, and I have a label here.
Earth masses. So we expected two small planets to super Earth. But also look at the hyperparameters that we found for the GP. The characteristic period of the GP is also in agreement with the rotational period of the star. So it's about 4 days. And also the long-term evolution timescale, it's of 114 plus minus 19. So this is also in agreement with these signals that we found in our frequency analysis. And we associated this with the lifetime of active regions on the stellar surface. Okay, so focusing on this ultra short period sub-Earth. Here is the mass radius diagram of a small ultra short period planet with masses and radii known with a precision better than 20%. So this world belongs to this handful of planets here and is also the smallest and densest USP known to date. Comparing to theoretical composition models, is also expected to have a composition of most mainly of iron, and taking into account also the very high density, very also precise, of 10.2 gram per cubic centimeters, that is 85% higher than Earth's density. We can say that GJ367b leads the class of supermercuries. So very extreme dense planet containing an excess of iron. So for this ultra short period planet, we performed some interior structure models given the high precision on the mass and the radius that we estimated. And we so from our results, we expect an iron core with a mass fraction of 91%. How to explain the region of this kind of planets? It's a very big question. So the formation evolution is still debated, and some formation pathways, so we have different formation pathways. One of these is that the planet formed out of more iron-rich materials in the disk, in the primordial disk, or it was a low-dense, larger planet, and then for some removals of outer layers, this differentiated like in denser core and low-dense outer layers. They were removed for some reasons. This reason could be for collision stripping or for stellar radiation. In fact, we have very strong stellar radiation. The planet is very close to the star. It has an equilibrium temperature of 1,300 Kelvin. So this temperature, the outer layers could just sublimate and transport it away from the surface of the planet. In addition to this, so I say that we found two other companions in the system. And actually, this is in line with the tendency of USP planets to have other companions, so to belong to multiplanetary systems. And actually, the presence of the two other planets could also be they could also be responsible for the migration of this planet so close to the star. So our idea about the formation pathway that could explain the system architecture is a high eccentricity migration scenario. So that due to chaotic secular interactions with the companions, the inner planet reaches high eccentricity and then approaches the host star close enough that it's tidally captured in a very short orbit. So the system is very interesting, and what is interesting is this is it could be one of the best targets to prove and to test the formation evolution theory of ultra-short period planet. So here are my conclusions, and I want to highlight that thanks to this long-term intense radio velocity follow-up, we were able to estimate high precise mass, radius, and density, and have a firm evidence that this sub-Earth GJ367b is a super Mercury. And also, we discovered two additional non-transiting small companions with orbital period of 11.5 and 34 days. Thank you.
Questions?
Hi, Mangesh here. Are these planets
Hi, Lisa, thank you very much. I'm Louise Nelson from ESO. Can you comment a little bit about the choice for the floating chunk offset for the inner planet and how the mass you derive sort of differs between doing that and then doing the multi-GP? Because as far as I could see in the numbers, the RV amplitude is significantly smaller when you're doing it through the GP, right?
So they are in agreement, but actually, as you said, from the GP, the semi-amplitude of these ultra-short period planets is a little bit smaller. But so we consider that like the GP maybe could like heat the signals of the ultra-short period planet, and consider that the floating chunk offset method. So we were able to, with our measurements, we were able to cover all the orbital phase of the planet, of the inner planet. And so with this method, we expected we can like remove all the other signals there are with longer period. So we can just like focus on the signals of this ultra-short period planet. And so yes, at the end we took as the results the results from the floating chunk offset method.